So thank you very much, Dennis, for inviting me and for the introduction. So I'm Erik Wang. I'm assistant professor at the Australian National University. Today, I'm going to talk about matching methods for causal inference with time series cross-sectional data. This is joint work with Kosuke Imai at Harvard and In-sung Kim at MIT. I just want to say that I feel extremely honored to be presenting this research with this group. Okay, so here's our research in a nutshell. We propose a matching method for time series cross-sectional data where we algorithmically create a match set for each treaty observation. And then we refine the match set with any matching or weighting method so as to balance the covariates for the control units and the treaty unit in each match set. And after getting this match set, we're going to apply a standard low-weighted difference-in-differences estimator. Right? So there are several advantages for our methods, and there is also a disadvantage, which I'm not going to tell you now. I'm going to tell you a little later, right? So if we think about causal inference with time series cross-sectional data, one of the workhorse, actually the workhorse method to analyze such data is the linear two-way fixed effects regression. And that had been the case until very, very recently, right? So unlike two-way fixed effect regression, our method uses matching, which is non-parametric, right? And which will give us a lot of good properties. And essentially it helps us reduce model dependency and further mitigates confounding. And it also offers us, because it's matching, a set of simple diagnostic tools that can help us really kind of evaluate how our method works, given the identification strategy before we actually estimate the data, right? Estimate the effects from the data, right? But we also have all the good things about two-way fixed effects. So we eliminate both the unit specific time invariant and time specific common shocks as the two-way confounding, which is, as applied researchers, we know that once we have a panel data set and we want to make any sort of close to causal claim about it, right? We want to first sort of take care of these two confounding, and our method does that as well, right? And relatedly, right, we kind of, our method was actually written sort of, our method was written in a way that kind of precedes the current ongoing literature in the econ literature on different-in-diff with staggered adoption. And we also go beyond that, right? So our method actually allows us to analyze any treatment distribution in your panel data as long as the treatment variable is binaries, right? So we don't have to worry about treatment assignment being staggered. We don't even have to worry about some units will have treatments that will reverse back to non-treatment afterwards. And I'm gonna elaborate on that later, right? So here's an outline of the talk. I'm gonna first talk about the motivation, and then I'm gonna elaborate on the proposed matching methodology, followed by a brief overview of the simulation studies. And then I'm gonna talk about the empirical analysis of one of the empirical applications in the paper, and then I will conclude. So matching methods have become part of a standard toolkit for social scientists. As a social scientist, we like matching because it reduces model dependency in observational studies, and it provides us with diagnostic tools to check how we perform with whatever method we use through balance checks, right? And it also helps us sort of just clarify the comparison between treated and control units. Right? However, almost all existing matching methods were developed to deal with cross-sectional data. Right? And so matching can be trickier for causal inference with time series cross-sectional data. Right? it's like intuitively, it's just sort of hard for us to envision where the control groups will come from, right? This is because the treatment assignment can be very complex in time series cross-sectional data. We have different units that will receive treatment at different times, the so-called staggered adoption. And then treatment could also reverse, right? So units can go in and outside of treatment condition at different points in time, right? But actually, matching representation is crucial for causal inference with time series cross-sectional data. One message I want to convey today is that through matching, we could actually, in a very principled manner, properly implement the very popular identification strategy with observational studies in the panel data, the two-period difference in differences identification strategy, right? So it's, as I will explain later on, it is really through sort of matching that diff can be properly implemented in time series cross-sectional data. And essentially our method is gonna just automatically locate all the possible two-period diff cases with matching algorithm in a long or short panel data, right? And so the paper has two empirical applications. One is the relationship between democracy and economic growth, studied by Asmoglu et al., published in Journal of Political Economy. Another one is the effect of interstate war on inheritance taxation by Sheeb and Stasovich in the American Political Science Review. For this talk, I'm going to focus chiefly on the first application. So the relationship between democracy and economic growth, especially whether democracy leads to economic growth, is a longstanding question in political economy. Asmoglu et al. In 2019 provides an up-to-date empirical study where they use a time series cross-sectional data set of 184 countries over 51 years, right? And then the main basis of their estimation framework is two-way fixed effect, right? Including country fixed effect and year fixed effect. And then their treatment variable is a binary indicator, taking 1 for democracy and 0 otherwise. So from our package, we can use the treatment variation plot to visualize the distribution of democracy as the treatment, right? So we see here that the x-axis refers to year and the y-axis refers to countries. So each tiny cell here is it's a unit time observation, right? It's a country year in the time series cross-national data. The blue cells are the untreated observations, right? The country years and their autocracy, right? And then red cells are the treated ones, right? The country years and their democracy. So we see here that the treatment assignment is like very generalized, right? Treatment can happen anytime, anywhere, but mostly there are, countries that have always been democracy, countries that have never democratized, but then there are countries that democratized early on, and then there are countries that were never democracy until recently, right? So this is a so-called staggered adoption in the econ literature. But this is more than just staggered adoption, right? Because we have both democratic transitions and authoritarian reversals, right? There are a lot of cases, a lot of countries and years where democracy can revert back to authoritarianism, right? So there are these kind of countries that become democracy and then become autocracy once again, and then becoming democracy again before switching back, right? So this is a very generalized treatment distribution. And so this kind of distribution should prompt us to think of identification strategies that rely on within unit over time variation, within time across units variation, or variation in the timing of treatments, right? The generalized diff, right? And so here I just put the treatment variation plot for the other application side by side with the previous one, right? So here we have, again, the countries on the y-axis, year in the x-axis, and then we have the war as the treatment, right, for several countries, right? And we see, again, there are different countries can receive the treatment differently, but importantly, treatment also reverses back, right? So because war doesn't last forever, right? So if we really want to understand the relationship between political institutions and economic growth, we want to understand both how becoming democracy affects growth and becoming not democracy, right? Or like becoming autocracy affect growth, because only the two, like both questions are important for us to understand this general inquiry, right? The relationship between democracy and growth. And if we want to understand the effect of war on taxation, we want to understand both the effect of war and the effect of peace, right? And this is just, I'm showing you another example. This is from my own research on the effect of anti-corruption inspections in the Chinese bureaucracy on bureaucrats' productivity, right? So this is because these two are just like country year data, but I'm showing you another example of more micro data set. So this is 72 months with 2,700 counties, right? So each cell is a unit time observation, a county month. So the red cells are the treated ones, right? Are basically the county months that are under inspection. The gray cells are the non-treated ones. And again, as with all other political science, as with a lot of other political science applications, treatment sort of comes and go, right? It switches on and off, right? So it's beyond staggered adoption. Right? So for this kind of applications where treatment assignment can be very general, right? It can come at different time and it can switch back and forth, right? How do we analyze it, right? So a standard way of analyzing is two-way fixed effects, right? So that's what we have been using until very, very, very recently, right? But it has been shown by Imai and Kim in an earlier paper and many after them that if we are using two-way fixed effect to estimate causal effect, right, in the potential outcome framework, it actually generally does not give us consistent estimates unless one of the following two conditions holds, right? So one is that treatment effect has to be homogeneous across units, which, as social scientists know, rarely happen in the real world because we know that treatment effect is heterogeneous, right? And another one is that the proportion of treated observations has to be constant across units. So this is another really weird assumption, which means that for the 50 countries, right, for all the countries that had democratized, right, we will require all the countries to have been under democracy for the same amount of years, right? Not necessarily the same year, but have to be the same amount of years, and that just doesn't really happen in the real world, right? So, and these findings are like related to a larger set of sort of revelations that highlight the very strong parametric assumptions in linear regression when we are talking about causal effect, right? So I'm just only giving you one example from the poli-sci literature here, but there are people, econometricians, sociologists, statisticians that have basically shown the same thing, right? And so, and then another traction for two-way fixed effects is that it's algebraically equivalent to difference in differences, but that is only true in the simplest two-period setting where nobody is treated in the first period and then some folks receive treatment but not others in the second period, right? And once we go beyond this simplest setting, two-way fixed effect is not different-diff, right? So different-diff does give you the consistent estimate for ATT, right, for average treatment effect for the treated, but two-way fixed effect is not different-diff in a longer panel data with slightly more complicated treatment assignment regime, right? And so recent works in the econ literature studying causal inference with time series cross-section data are largely devoted to understanding how we could still use sort of different-diff in a sort of multi-period setting where treatment assignment timing differs across units, right? So there are, as I think, as people who are interested in panel data all know, I mean, if you guys are on academic Twitter, right, it's all about it, right? Like all of it, like staggered adoption, difference-in-diff, right? So, but all of these works, you know, require that once the units are treated, you know, treatment assignment can happen at different times, but once you are treated, you remain treated in the following period, right? So this is just, I'm just taking a picture from AP Inbins, right? So this is basically staggered adoption, right? So the x-axis is units, y-axis is units, x-axis time. So you have units that are never adopting treatment, that have never adopted treatment, the never adopter, and then you have units that were treated early on, the unit that were treated, you know, in the middle of the period, and then you also have unit that didn't get treated until recent, right? But the key assumption here is that once a unit is treated, it remains treated forever, right? But we know that, like especially in political science applications, we don't have these settings in general. We have more complex settings where treatment can reverse, right? So now I'm going to talk about our unifying matching framework that basically can handle this kind of both the staggered adoption, non-staggered adoption, and the more complex and more generalized case of treatment distribution. Right? So the researcher gonna make two decisions. One is to choose the number of lags for confounder adjustment, and this gonna come in handy for the identifying assumption and a later step in our package. And then she's also gonna choose the number of leads denoted by F, which indicate the time period at which your effect estimate going to be measured, right? So if I want to look at the effect 4 years later, right, we will set F to 4. If we want to look at the contemporaneous effect, we will set F to 0. So this way, it allows us to sort of flexibly analyze both short-term and long-term effect, right? And then so the quantity of interest is the average treatment effect of policy change for the treated, right? So just with any sort of panel data causal inference, we are looking at basically the treatment effect for the switchers, right? So for those who are authoritarian regime at time t-1, but switching to treatment conditional democracy in the current period, right? And so there are several assumptions. So the standard assumption of no spillover effect applies here. And then we allow for a limited carryover effect, right? So the standard assumption is no carryover effect. So basically past treatment shouldn't affect outcome, right? But we allow for a limited carryover effect within the past L periods, right? So we allow for past treatment within the L, within the lags that the researcher choose to affect outcome, but just not after the L period, right? Just not further back, right? And then the identifying critical identifying assumption is parallel trend, as with difference-in-diff, conditioning on treatment history, right? Conditioning on treatment history up to L, right? So the pattern of the treatment status in the treatment variable up to past L periods, and conditioning on past outcomes and past conditioning on past outcomes and current covariates and past covariates up to this L, right? So this F here is basically important for substantive interest, and L here, right? L here is important for the identifying assumption. And as I was talking about treatment reversal, we can basically easily write the quantity of interest and the parallel trend assumption by just reversing the notations to get the same sort of ATT for the reversal, which we call the average treatment effect of policy reversal for the treated, right? So we are looking at basically the reverse, right? So here we are looking at the switchers, right? Effect among switchers. Here we're just looking at the effect among the reverse, right? So people who are like countries who are democracy today but becoming democracy, were democracy yesterday but become democracy today, right? And so the second step is to construct a match set for each treaty observation. So I'm going to define the treaty observation as an observation where it is sort of where the value in the treatment variable takes 1 for the current period, but takes 0 in the period right before, right? So that is basically a switch, right? So that is a treaty observation, and our match set is gonna contain all the control units that share identical treatment history of the values, the 0, 1s in the treatment variable up to L, right? So from time t minus L to times t minus 1, we're gonna have a control unit that basically has the same values, same sequence of treatment values with the treated unit, right? And that is in the control, that is basically in the match set for that treated observation, right? So if this is unclear, I'm gonna explain that with examples in a bit, right? So, and if we set the treatment history to be very long, if we set the L to be very long, there are going to be treated observations that will have empty match sets because there are very few other units that will share the entirely same long treatment sequence before T, right? So that way, when we're actually using the method, we should notice that the kind of the quantity of interest kind of change a bit, right? So it's not just a treatment effect among the switchers, but it's a treatment effect among the switchers that have a control group with the sort of the L set by the researcher, right? So this is similar to the risk set in the biostats literature, except that we do not exclude those who already received the treatment, right? And so here are two examples of match sets for ATT and average reversal effect ART, right? So here we have units I1, we have treaty observation at I equals to 1 and T equals to 4, right? Why? Because this unit I1 was 0 in the treatment variable is 0 for T equals 3, but switching on to 1 in T equals to 4, right? So our algorithm gonna identify all the treaty observations like that, right? And then for each treaty observation like that, we're gonna search for all other units that share the same treatment history, right? So here the researcher sets the L to 3, right? So we're looking at the treatment variable for the past three periods. So for this treaty observation, the past 3 periods 0, 0, 0, right? And now we're gonna find all other units that remain untreated in the same time period, T equals to 4, right? So we have, both I2 T4, right? Because this is also 0, 0, right? Rather than 0, 1. So you remain untreated. And then we have I4 T4, right? 0, 0. And then we have I5 T4, also 0, 0 in the same 2 periods, right? But then we're gonna look at the treatment history, right? So the treatment history for the treated observation is 0, 0, 0 for times 3, 2, 1, right? So, and then our algorithm gonna find both units I at T4 and units 4 at T4, right? Because these two units also have treatment history 0, 0, 0 for times 3 through 1. And this guy, I equals to 5, is not a match control unit in the match sets, unlike these two, right? Because even though it remains untreated, right, from 3 to 4, its treatment history is 0, 0, 1 rather than 0, 0, 0, right? So essentially we have this treated observation and then these two sequences as the match control units in the match set, right? So, and then we will have, let's say there's another treated observation, right? T equals to 3 and T equals to 4 for unit 3, right? Because unit 3 treatment status was 0 in time T3, but switching on to 1 time T4, right? And then we're gonna check the treatment history. The treatment history for the past 3 periods is 0, 0, 1, right? And then this guy, I equals to 5, who was not a match control unit for this treated unit, is now qualified for being in the match set for this treated unit, right? Because they have the same treatment history, 0, 0, 1, right? And then we can have another guy, right? Another treated observation that is I equals to 2, t equals to 5, because the treated the treatment variable switches from 0 to 1 between times t equals to 4 and equals to 5, right? And then we're going to immediately, right, check the treatment history, 0, 0, 0 for times t equals to 4 through 2, right? And then we're going to find all other untreated observations, like all other 0, 0s for t equals to 4 and 5, right? So I equals to 4 and 5 are the potential candidates. And then we check their treatment history for the past 3 periods. For the past 3 periods, they both have 0, 0, 0, identical to the one in the treated unit for this time period, right? So then these two are going to be in another match set for this treated observation. So each treated observation is going to have a match set that contains all the match control units sharing the same treatment history. And we can see from the right panel how how our method can be easily used to analyze treatment reversal, right? So in the reversal case, right, we are looking for switching from 1 to 0 as the treated observation, right? So for example, unit I equals to 1 here, it's treated, quote unquote treated, or I would say substantively reversed, right? Because its treatment value switches from 1 to 0 between the 4th and the 5th period, right? And then and then the untreated observations in this case will not be the 0, 0s, but the 1, 1s, right? Because this is, for example, this guy, right? Unit I equals to 3 times 5 and 4. The treated observation is basically the reverse one, right? From 1 to 0, and this guy basically doesn't reverse. It remains treated from 1 to 1, right? So then this is basically like a potential candidate for a control unit in the match set for this guy, right? And then we have the treatment history 1, 0, 0 for the past 3 periods, and this guy also satisfies. So this unit gonna be part of a control, gonna be a match control unit in the match set for this treated observation or for this reverse observation, whatever you call it, right? And there are going to be cases where you have a treated observation, but the match set is empty, right? So for example, we have this treated observation, right? T equals to 5 and t equals to 6, right? So it switches back from 1 to 0 in these two adjacent time periods. So this is basically a treated observation for the reversal case, right? But then there's no match control unit, right? Even though there's an untreated observation, right? Because it remains treated in the following period, unlike this guy, right? The treatment history is different, right? So the treatment history for this guy is 1, 1, 0 for the past 3 periods. But then the treatment history for this is not 1, 1, 0, 1, 0, 0. So they don't share the same treatment history up to past 3 periods as the researcher stipulates. So this treated observation is basically going to have an empty match set. So it's not going to enter into estimation, right? So this is an example from the real data set, right? Where we have Thailand, who is treated in 1978. So Thailand 1978 is a treated observation because it was a democracy it was an autocracy in 1977, but democratized in 1978, right? There's a switch between 0 and 1, right? And our algorithm going to find Argentina, which remained untreated in 1978 because it was autocracy in 1977 and autocracy remaining so in 1978. And Argentina share the same treatment history. So here the researcher sets L to 4, right? So we're looking for a past 4 periods for the treatment pattern. So the treatment treatment history for Thailand before 1978 democratic transition is 1, 1, 0, 0. Democracy, democracy, autocracy, autocracy. So we have Argentina being a match control unit in the match set for Thailand 1978 because it shares the same history: democracy, democracy, autocracy, autocracy, and then remaining autocracy rather than switching to 1, right? And this is an example from my own research. So we have I'm showing you these examples because in a lot of times we have the treatment history being like 0, 0, 0, 0, 0, right? But I'm showing you some specific examples where the treatment history can have ones, right? So here, county UC is treated in January 2015 because its inspection status switched from 0 to 1 between December and January, right? And then so we identify that as a treated observation, and then we identify the treatment history, which is 0, 1, 1, 0, right? Which is a pretty weird sequence, right? 0, 1, 1, 0. And then we search across the entire data set for counties that remain uninspected between December and January, but otherwise share the same past inspection history for the up to 4 time periods. So we have Guangzhou and Mengla, which also share 0, 1, 1, 0 for the past inspection. So therefore, these two counties for these periods are going to be the match control units for the match set for UC in January 2015. So after we get the match set, we're going to refine the match sets by making additional adjustment for covariates and also, if you like, past outcomes. So this is a step in our method where we basically control for observables, right? And we can use any weighting or matching method to adjust for these covariates within each match set. So our package offers 2 classes of methods. One is Mahalanobis distance matching, right? So where we basically calculate the distance between each control unit in the match set and the corresponding treated unit for each pre-treatment time period, small l, right? So the small l is basically one of the pre-treatment time periods in the big L, right? So if we set the past history to 4, we are going to look at a t-1, t-2, t-3, t-4, right? And so we're going to do that for all the covariates in each pre-treatment time periods within each match set, and then we're going to average this measure across the L, across all 4 periods, so that we will have one number measuring the distance for each. So each match control unit will have one number measuring its distance to the treated unit in the same match set in terms of the covariate, right? And then after we get these numbers for each control unit, reflecting the similarity in terms of covariates, we can just pick the J most similar match control units and drop the rest, right? So essentially, we are refining a match set by shrinking it to include only the control units that are the closest to the treated unit in terms of Mahalanobis distance based on the covariates. Okay. Another way is to do it through propensity score matching or weighting. So here we basically pull all the match sets together, and then we estimate a treatment assignment model so that we will have the coefficients for the covariates in the propensity score model, right? And then we use these coefficients to go to each match set individually and multiply with their covariate values, so that we again will get one number for each match control unit within each match set, reflecting its closeness to the treated unit, right? So once we get these scores, right? Once we get these scores for the control units in each match set, we can just do the same thing as with Mahalanobis distance by basically picking the top J closest control units in terms of propensity score to the treated unit that reflect covariance, right? And then drop the rest, right? Or we can still keep all the match control units in the match set, but essentially using the score as weights, right? So rather than shrinking it in the weighting scheme, we will have all the control units still in the match set, except that those with higher similarity will receive higher weight in the estimation later on, right? So here's an example that we can visualize from our R package, right? So here is Bhutan in 2008, experiencing a democratic transition, right? So this is a match set before refinement, right? So here we have Bhutan switching to democracy, and then all these other countries that share identical treatment history, which is all zeros, right, for the past 4 periods, right? They are all in this match set, right? So here is the match set after propensity score weighting scheme, right? So here, essentially, all the match control units in the match set still remain, right? But it just that the closest ones to Bhutan, right? In terms of the covariate value, will receive higher weights indicated by darker blue color, and then the sort of the less similar ones in terms of that propensity score will receive lower weights, right? And here is an example where we shrink the match set. So here we use Mahalanobis distance, for example. Now we're gonna basically pick the top 5 closest countries within these time periods to Bhutan 2008, and then we drop the rest, right? So here, all the 5 match control units are going to receive the same weight, right? So they are going to be equally weighted, right? Because they are all closest. We are just going to artificially pick the top 5, so each will receive an equal weight, right? Okay, so after we get these weights, whether continuous weights through these sort of weighting scheme or equal weight through a matching scheme, picking the top J. After we get these weights, we can now proceed with the final step, which is a weighted difference-in-diff, right? So essentially, for each match set, so each match set is basically a smaller data set with 1 treated unit, and all others are control units with weights, right? And we're basically going to construct like a synthetic control using the weights from all these match control units. And then we're going to subtract, basically take the difference between the treated ones and the synthetic one, right? And except that here, we are doing difference in differences, right? To basically purge out the two-way fixed effect, essentially, right? So essentially, we are going to take the dependent variable value for the treated. So for each, I'm talking about 1 match set, right? So we're going to take the difference between the dependent variable value for the treated unit at time f, right, and the dependent variable value for the treated unit at time t minus 1, right? So that's basically the first difference, right? We're going to do the first difference for the treated unit, and then we're just going to take the average of the second difference for the control units, which is that we take the dependent variable value for the all the control units in the match set for time t plus f, and then subtract from that the dependent variable values for all the control units in time t minus 1, right? And then we take the average, except that we're going to take the weighted average here, right? And then the weights are the weights that were constructed based on the refinement that I have just shown you, right? So basically, for each match set, we're going to just take a weighted difference in the 2 differences, right? And then after we get a different diff for each match set, we're going to just simply average them up to get the overall different diff estimate for the ATT. Right? So and that's the same with average reversal effect. Right? So and then we use a block bootstrap for standard error. Right? So here's an example of from the data set with the weights, right? So here is a hypothetical example where I use propensity score weighting, right? So we have a treated observation Argentina 1983 because it was autocracy in 0, and then it was autocracy in 1982 and becoming democracy 1983, right? And then Mali, Chad, and Uruguay basically are the match control units for this country because they share the same past 4 period democracy status, which is all 0, right? And then the match set, if you use propensity score, we're gonna have the coefficients for the covariates, and then we're gonna multiply that with the covariates to construct a weight, right? So here, basically, we have the Uruguay who has a higher propensity score, therefore receiving a higher weight, and then the Chad and Mali gonna receive sort of slightly lower weights, but all all of them are going to be in the match set, right? And then we're just going to take the log. So the dependent variable is log GDP. We're just going to take the log GDP for the in 1983, and then subtract from that the log GDP in 1982, right? So we have the first difference for the treaty observation, and then we're going to have the weighted average using this weight of the differences between log GDP 1983 and log GDP 1982 for all the control units, right? And then we take the difference in the differences, right? So that we have basically a weighted different diff for this match set, and we're going to do that for all the match set and then average them out, right? And so after we have and then because we are using matching, we are able to have sort of a balance metric that can help us visualize and assess balance, right? So the balance for each covariate J at pre-treatment time period T minus L in each match set is essentially the difference between that covariate, the difference between the covariate value in that time period for the treated unit and the weighted average of those covariate values for the in that time pre-treatment time period for all the control units, right? So we're gonna have basically for each match set, we're gonna have sort of a balance measure for each covariate in each pre-treatment time periods, right? And we're gonna divide that by the standard deviation of the covariate values for all the treaty observations across the data set for the same L, right? So that way the balance measure is basically in terms of standard deviations, right? And but this is just like one balance measure for one covariate in one match set for one pre-treatment time period, right? And then we're gonna get a bunch of measures, but to better evaluate, we can have a sort of a average measure, right? So we can average this measure across all sort of match sets, right? So essentially, we're gonna have for each covariate in the data, we're gonna have a balance measure for that covariate for each time pre-treatment time period. So for T minus 4, T minus 3, T minus 2, T minus 1, we're gonna have a measure telling us how good the balance is for each covariate. And later I'm going to visualize the line plots and the scatter plots so we have a better like a clearer idea, right? So let me first show you the simulation studies. So so here we make simulations realistic by basically taking the original data set used by the Asmoglu et al. And so we essentially impute the missing values in the original data set so that we have a balanced time series cross-sectional data with 162 units and 51 time periods. I'm emphasizing that like our method can work with unbalanced data set as well, but just for the simulation purposes, we're gonna use this sort of balanced data. And then we essentially, basically we have this kind of real data, right? Except we rebalanced it, and then we're gonna fit the following models to the balanced data, so that we will have the coefficients, right, as parameter values for the covariates, and the past treatment. So basically both the treatment and outcome model include the two-way fixed effect gamma, the gamma t and alpha I, right, and also the past treatments, right, up to L equals to 3 here, right? So, and then also have covariates, right, and some interactions among certain covariates, all up to all lap for each of the pre-treatment time periods, right? So essentially we feed these two models. So these two models contain basically lag covariates, current covariates, and lag treatments as confounders, right? And we fit and also interactions among among covariates, right? And we fit these two models to the real data, to the real rebalanced data. And then we're going to get the parameter values, right? And then we use the parameter values to regenerate new simulated data, keeping the covariates values as fixed, right? And so I want to emphasize here that this setting is favorable to OLS because the data is generated with linear models, and we're going to focus on 3 settings of misspecification, right? So basically the truth has basically 3 lags for lag treatment and lag covariance, right? The severely misspecified case is where we only control for 1 lag for the OLS with 2 fixed effect, and only sort of match on past 1 period for treatment history in our method. The moderately misspecified case is where we basically set L to 2 for our method, even though the truth is 3, and then we include 2 lags in the OLS, right? And then we have the correctly specified case, right? So basically, in the misspecified cases, our method is also misspecified, right? And here we basically show the biases in terms of box plots. So for these two, the first and second column are OLS and OLS with dummies. So OLS with dummies is another way to control for lag treatment, as suggested by a reviewer. But I can talk about the detail in the Q&A. But basically they have the same results, right? So essentially, what we are seeing here is that our method basically completely outperform OLS in the severely misspecified and moderately misspecified case. But obviously OLS return the truth more efficiently in the correctly specified case because the data is generated with linear models, right? So and here we basically also present sort of balance all the balance measures from the simulated data set. So this is the balance across all covariates for each case. So for this case, for example, we are using propensity score, and then we have and then this is sort of balanced covariates for each pre-treatment time period, right? Small l for the correct specified case and the moderately misspecified case and the severe misspecified case. So essentially, we have a pretty good balance. Our method can achieve pretty good balance, especially in the moderately misspecified and correctly specified case. So most of these balance are within the 0.2 standard deviation, which is a rule of thumb, right? And but there's a bias variance trade-off for our method. So here I'm reporting sort of results for power, right? So power is calculated as 1 minus the coverage rate. And here we set the true beta from -1 to 1 so that we can basically visualize sort of how the power sort of evolves, right? So essentially, and these lines, so this sort of the 2 lines, this sort of red and blue line here, because they have the same result. Basically, there are 2 ways to control for lag treatment for OLS, and they have the same results. And then they basically are very off, right? So the power for OLS is actually very off for all the truths in the misspecified and the moderately misspecified case, because they suffer huge bias, right? And for our methods, we perform pretty normal, like the pattern is pretty normal. But if you look at the correctly specified case, we see that the OLS are actually very efficient, right? So basically, when the truth is 0, they have full power. Like they don't really cover. But so if we look at this, right, when the truth is -1, our methods basically, any matching or weighting technique basically means that we sometimes can, even when the truth is -1, we can cover, our confidence interval may cover 0 for like up to 60 or even 80% of the cases. So this is a very conservative method, right? So basically the power is kind of much smaller for our method, and the OLS is much more efficient in the correctly specified case, even though in reality, there's no correctly specified model, right? So this basically means there's a bias variance trade-off, and this makes sense intuitively because our method, you really focus on match sets, right? We're basically pruning out a bunch of data. We're pruning out the data without match set, and then with the match set, we also pruning out or at least downweigh a lot of observations, right? So that's why our method is conservative. And I think for applied researchers, it's not necessarily bad news. So if you analyze your own data and then you have a hypothesis and then you have results sort of supportive of your hypothesis using our method, then you can just say that this is even better, right? Because our method is more conservative. So we should feel safer when we have results supportive of our hypothesis using a very conservative using a conservative method, right? And so let's quickly move to the empirical analysis. So we're going to analyze the Asimov democracy and growth and growth data. So the title of the paper is "Democracy Does Cause Growth," but the dependent variable is not growth. It's just log GDP per capita. It's the level, right? But anyways, so we're going to focus on cases where we set L to 4 or 1, right? So we're going to use 4-year lag for the treatment history and 1-year lag, right? And then we look at the effect, the contemporaneous effect, and longer term effect up to 3rd and 4th period, right? So, and then we're going to analyze both democratization, authority, and reversal. So our method our package basically allows us to evaluate matching before we proceed with a refinement, right? As I said, this is a conservative method that requires a lot of information from the data. We can examine basically whether we have enough information, right? So here in the left histogram, we have basically the distributions of the number of match control countries in across match sets for both 4-year lags and 1-year lag, right? And we see here, so basically, if we use like 4-year lag because the pre-treatment treatment history is longer, we tend to have some treaty observations that don't have any match control units, right? So in the democratization case, if we match on past 4 periods, there are going to be 9 treaty observations that are going to be dropped, right? And for the authoritarian reversal case, we're going to have to drop 5 treaty observations because they don't have match control units, right? But we see from this histogram where the pink bar is for the number of match control units for the 4-year lag, white bar for 1-year lag, we actually have good amount of information that we can use after matching, right? Because the majority of the match sets actually contain more than 60 countries, right? Even for the 4-year lag. For the authoritarian reversal case, the majority of the match sets contain more than 25 countries. And when we use Mahalanobis, we're gonna pick the top 5 or top 10, and that means that we have enough observation, we have enough information to choose from, right? So here I'm gonna show you improved balance. Again, this is something that can be done with our package. So the left panel is democratization. The right 2 columns are for authoritarian reversal as the treatment, right? So the 3 columns are using Mahalanobis matching, use propensity score matching and propensity score weighting, right? And then the x-axis is basically the standardized mean difference between the covariate period for the control and the covariate period for the treated before refinement, and then the y-axis for after refinement, right? So each dot here is a covariate for a pre-treatment period, which is why for the 1-year lag graph, we have a smaller number of symbols, right? Because we only have because the small l is 1, right? So we have, for example, trade as a covariate for the past 1-year lag, right? But for the 4-year lags, we have more symbols because we will have trade in time t-1 and trade in time t-3, trade in time t-2, right? So we just have more symbols. This is just to clarify why there are more symbols for 4-year lag than 1-year lag. But essentially, we have achieved balance pretty well here, because the balance essentially heavily tilt these symbols downwards below the 45-degree line, right? So basically it means that the balance improved quite a bit, especially for propensity score weighting, right? After refinement, right? And this is another way to visualize the balance. So here we have the line plots for each covariate, right? So this is basically each covariate at each time period, how good the balance is, right? So the top route is for democratization, the bottom route is for authoritarian reversal, and we see that before matching, right? So the gray lines here are the covariates. The black line here is the trajectory of the dependent variable, right? So basically before matching, there are a lot of difference between between sort of match and potentially control units up to past 4 time periods. And then after matching, right, the balance doesn't improve much, right? Even though the lines are flatter, right? So the real improvement in terms of balance come after refinement. So we see that in all 3 classes of method, Mahalanobis, propensity score matching, propensity score weighting, we managed to shrink these quite a bit, right? We would basically the treatment and the control units after matching and refinement become quite similar in terms of their covariate trajectories and the past and the outcome trajectory for the past period, right? And here after we get these weights using this refinement, we do a weighted diff for each of the both contemporaneous periods and the future periods up to the 4th year, right? And in the top row, we report the results for the effect of democracy on log GDP, and there's no effect, right? But to paraphrase Acemoglu's paper title, "Democracy Does Cause Growth," we actually agree, except that it causes growth in the following sense, right? In the sense that it's not democracy per se that improves growth, but backsliding into autocracy actually hurts growth, right? So this is something that we can find using our method, because we can distinguish between the ATT and ART case, right? So I think this finding is interesting in light of the rapidly proliferating literature on the economic implications of democratic backsliding, right? Okay, so to conclude, matching is a transparent and simple method for causal inference, yet it has not been applied quite much to time series cross-sectional data. And here we propose a matching framework for such data. We construct match set, and then we refine the match sets using existing methods. And then after we get the weights, we just apply a weighted difference, right? And then so we also allow us to check covariates, and then we compute standard errors for the estimate. And then all the methods can be implemented using the R package that I've made. So in the ongoing research, we are addressing sort of possible spillover effects, possibly by matching our neighbors' treatment history. And we are also trying to take a stab at the continuous treatment case, right? So the reference here is the AJPS article, but then there are 2 related papers that basically by Imai and Kim that basically highlight the problems with 2-way fixed effects for causal inference, to which our current article provides a solution. Yeah, thank you very much.
Perfect. Thank you so much, Erik. Super insightful talk. We now have roughly 25 minutes for questions and answers. Just as a reminder, if you unmute yourselves and speak, your question will be recorded, as we are recording today's meeting in active speaker mode. You can also post your question in the Zoom chat, either for everyone to see or as a direct message. While we wait for more questions to come in, I've actually already received a set of questions, Erik. So I'd like to address those to you. I'll read them out anonymously, given that those were sent to me by DM. The first question is there, considering that you can also use panel data analysis for cross-sectionally clustered analyses, such as students clustered in classes, is there a way or even a need to cluster observations in such larger clusters when using panel match?
I believe we can. So the question is about. So for example, if we have cities and states in the United States, right? And if in the panel data the unit time observation is a city year, but then somehow we wanna have cluster standard error for states, right? Is that the question?
Yes. So for example, if you have in your example, if you have state level covariates that change over time, maybe even the treatment effect of interest is a state level covariate, would you have to adjust for that and by clustering somehow, and how would you do that?
Right. I think so our package, I mean, currently we don't have sort of cluster standard error option for the larger for the larger cluster, but that can be easily incorporated, right? But I don't get the question about. So that's a standard error issue, right? So and that can be easily incorporated. And then the estimation issue. What? So it's. Can you elaborate on that? The estimation.
I don't know.
Yeah,
so
I mean, you can just
like.
So, anyways, so the covariates, right? You know, even the covariates don't vary at the lowest level of unit. It can vary at the higher, at the medium level units like states, right? And you can still sort of include that covariates in as refinement in the match set, like that. You know, you can still do that. Just as if if you're running a regression, right? There are covariates that only vary at a higher level, and you can just throw them in. Yeah, and you can do that with our method as well. Yeah.
Okay, perfect. The other questions that I received via DM, I think I can group two of them together. What are your thoughts on using panel match for panel survey data, especially when dealing with unequal interviews or unequal spacing between interviews? So I guess essentially unbalanced panel data.
Right. Yeah. I mean, they can. Yeah. So essentially, for survey data, it's basically individual. It's basically individual. I mean, it's basically individual fixed effect, right? So basically, each treated unit is like an individual, right? And then I mean, the empirical analysis we did here is also with the unbalanced data. The country year data is also unbalanced. And then the individual, if you have an individual survey, and if you wanna, so my understanding is that if you have panel survey, then so there are researchers who don't use individual fixed effects with panel survey, which I think is weird. But I think once we have individual panel survey, we should always, if you want to use OLS, you should always have the lowest level of fixed effect there, right? So I think, and then that's basically for panel match. So panel match basically, it's basically you match on an individual's past history. So basically it's like at the lowest level. So as long as so any data, any treatment pattern, you can do that with panel match, right? But it's basically like unit fixed. It's basically unit fixed effect, right? So it's yeah.
Well, I'm not sure if that was what the question was getting at, but I think one of the problems that might occur when you use unbalanced panel data is that what you would consider the first order lag might not be at t-1, but at t-2 or t-3 if you have missing waves in between. So would you match on the same years or just on the same order of lags?
I think that way you have to, yeah. So I have experienced those sort of situations. So that way you basically have to redefine time. So essentially, for this method to work sort of very well, you basically have to have like you want to avoid the gaps in the time. So basically, if for example, if you have 3 waves that come in in March, June, and September, right? Then you kind of want to use quarter as the time period so that it's like so that there's no gap. And if you continue to use month, then they're going to be like basically unbalanced in a very patterned sense, and that will be weird, right? Yeah.
And just as a follow-up, because the person who asked the question just specified their inquiry, would you consider it a problem, I guess in general, but for your method in particular, if your waves were unevenly spaced? So if you had interviews, let's say in February, November, and December?
Oh, I see. So for example, February, right? So right. So that's, and then but then what's the treatment? So I know that there are waves of people being interviewed. Okay, so for example, there are some treatments happening in November, right? So in that way, I think you just have to like redefine time in a substantively sort of meaningful sense, so that there are like no pattern gaps in the time periods. Yeah.
Perfect, thank you. There's one last question that was posted online, and it concerns the question of the ART.
Right.
And in particular, the person asks if it is possible to redefine the ART in a way that up to a certain number of leads, you only focus on those cases that reverse back into the control condition and stay there. So that essentially that in matching, you're not including those in the match set that reverse into the control condition and then switch back into the treatment condition, but that you, in a way, I believe, subset your estimate such that it only focuses on those individuals that revert to control and stay in control up to a number of pre-specified leads.
Yes. So you are saying, so for example, well, so basically this person is only interested in the countries where there are multiple reversals, right? So basically you were treated and then you reverse and then you reverse again, right? Is that so? Yeah. So I mean, I think the ART, the way we see it, is basically like any reversal is included, right? So that way we basically preserve the maximal number of amount of information. And if you want to further restrict that definition, you will have to just redefine the data in a way, right? So essentially you can, well, so you will have to only, for example, say that this is an easier way that I can envision is to have an indicator variable, right? And then you can match on that variable. So that indicator variable will be country specific, right? So there are countries that satisfy that person's question, and there are countries that don't. And then in our package, there's an exact matching option for certain covariates, right? And you can include that, right? So that's the way I can think of. But I wouldn't recommend sort of changing, like redefining the quantity of interest. But if you want to do that, there are ways. Yeah.
Perfect. Thank you. Next question. So we have two raised hands in the Zoom chat. First up is Kunli. Please go ahead.
Hello. Thanks so much for your very interesting and very clear presentation. I was just wondering, so about the length of the lag, the length of the match set.
Right.
So how do you decide that? Is that a researcher's arbitrary decision, or is there an algorithm that selects
right.
the optimum length?
So yeah, great question. So this is currently a researcher's decision, and then the trade-off is basically the longer the history, the more robust to confounders, right? Because you are basically looking at countries that were so similar because their treatment status was for so long a history, right? And then another downside is that it will restrict the drop more information. Yeah. So so basically for my own research, I use sort of both 4 lags and 6 lags as sort of showing that my results are robust to both. And then in other research, I recommend that people kind of just show that the results are robust to sort of different lags. Yeah.
Oh yeah, so I have actually a related question. So you construct the matching set based on your decided lag, and also you refine that with your covariates using a matching method, and then that makes even smaller sample size, right? Smaller size of the sets, right?
Right.
So how would you say, like, how robust would that be? Like, I mean, do you have any like any criterion on like deciding like the sample, trade-off between the sample size and
right? So I think if you have, so I think if you are picking, so for example, in this application, I mean, we don't have like we don't have like a rule of thumb here, but essentially we are using for example, we are picking the top 5 and top 10 and then drop the rest, right? So here we believe if you use 5 and 10, then I think so this kind of distribution where most match sets have more than 25, it will be okay, right? So it's like a 20%, right? So that will be okay. Obviously, if you have like even smaller sets, then you wanna only like look at, for example, top 1 and top 5, right? Something like that. Yeah.
And you have observed like there's more bias when there's smaller sets.
So there's well that we haven't, so we haven't necessarily observed well, there's actually more, the in applied cases, for example, there's more sort of variance with when you pick sort of only top 1 or top 3, right? So like you have larger confidence intervals. Yeah.
Okay, thank you.
Great, thank you. John Collins is up next.
G'day there, Erik. Can you see and hear me okay?
Yeah.
Okay, brilliant. Hello from another ANU person. It's really nice to see that this kind of cool research is being done over at ANU. So it's a really interesting model. And I just wanted to try and understand it a little better. And my question here is whether seasonality is kind of accounted for indirectly through your similarity scoring. So if so let's, we've got 2 things in a matched pair, and because their sequences are both 3 zeros and a 1. And then we apply the similarity scoring to them. Now, would the similarity scoring take into account, say, for example, that country A, had that sequence of events occur in the 1940s, and country B had that sequence occur in the 1990s? Does it take into account the seasonality here, so that countries that underwent this unique sequence occurred closer together in time, in real time?
Well, because our match set are only sort of focusing on countries with the same, we are basically operating with the same time periods, right?
Yeah.
So you are saying, I think.
Oh, okay. So it does. It only matches sets where they occur within like the same.
Yeah, within the same, right? So for example, like in the Argentina, like in the Argentina match to Thailand case, right? So we are not just looking at just 1100, right? We are looking at 1100 for the same 1974 to 1977. Yeah. because that way it will help us to take care of the season fixed effect or year fixed effect when we do the different diff, right?
All right, then if you don't mind me asking, how do we have any kind of overview of how many let's just say like democratization events, switching from autocracy to democracy, how many did and didn't have matches? How many how many matched groups were there of like one?
Right. So here, so for example, so here we have in the democratization case, we have like nine democratization episodes that don't have any matches, right? So that's indicated by the small bar here. And then
that's pretty good. Yeah.
Yeah, and then there are like 12 with like a small number of matches, but most of the things are like having, most of the democratization episodes have like more than like 40 matches. Yeah.
Okay. Wow. Yeah. Very good. Cool.
Thanks.
Great answer. Thank you.
Thank you.
Perfect. Thanks. Do we have any more questions from the audience at this point? Okay, so while we wait for potential questions to come up, I'll throw in 2 questions of my own. They're both related and also relate to what John just said. The first is, and I guess I'm trying to be the annoying person here who asked the question about the trade-off between external and internal validity. But how large a problem is it that matched sets may be based on selective and different sets when we look at the ATT and the ART? So in your case, as you just discussed in the democratization example, you were able to match most treated observations with at least one control. But you know, I wonder in other applications, it might be that more observations drop out because you don't find a suitable matched set. And it might be that those are fairly particular cases, right? So in the sense of democratization, for example, I could imagine, you know, going back to Huntington's work about the waves of democratization, that there are some cases that democratize or slide back into autocracy outside of these waves, which may be particular cases that are then systematically excluded from the analysis. And the estimate of the ATT and ART may be based on different subsets of cases then. So should that have us worried?
So, you know, there's always a trade-off, right? And then I think a more restricted number of available observations will just make the estimation more conservative, right? So, but I think for your particular question, that's actually, so for your very particular substantive example, right? In terms of democratic waves, that actually shouldn't make us worried because let me just. So for example, like even for some countries that democratize not with waves, right? Like for example, this guy, right? We know that the 70s is like a wave, and then the 2000s is like a wave. So for this guy, like when there's a decade in the world where only like one country democratized, but others didn't, because that country didn't kind of endogenously democratize, not being part of wave, that just means that that country has even higher number of controls, right? Because if you look at this, she switched from here to here, and then there are a bunch of countries that didn't democratize, right? Bunch of them didn't. The blue are the autocracies, right? Didn't democratize. So all of these are going to be part of the control units, and for those that did happen in waves, again, you have like we have like 160 countries. For example, 10 countries happen in one wave. That just means that 10 countries themselves wouldn't be control units with themselves, but then they also have a larger set of countries that didn't happen. Democracy where democracy didn't happen, so that can also contribute to the match set. So I think I get your question, and I think the challenge to external validity doesn't sort of manifest itself in the wave versus non-wave, but it could manifest itself in sort of other more, you know, other kind of situations that we probably don't have off the top of our head. So in that in that scenario, I think we should be more cautious. But then without this method, if you use OLS, then there are different observations are also weighted kind of weirdly to right. So we also we might suffer similar problems. Yeah.
Perfect. Thanks. Just the follow-up related question that I had in mind. What would be your practical advice to somebody who uses your method and runs into problem with finding suitable sets of treated and control units due to the scarcity of units that share identical treatment histories in the exact same year? Is there any way of coarsening this exact matching on treatment periods and lags or treatment histories?
So by coarsening, you mean like, for example, allowing, so for example, if the treatment history is 1100, we don't require the same history 1100, but we could relax the requirement, right? So for example, have 2 1s and 2 0s, but it doesn't have to follow that exact same order. And that, I will assume, will increase the number of qualified match control units. That's sort of what you mean by coarsening the requirements, right?
Yeah.
So currently our package doesn't do that, but I can discuss this with my collaborators and see whether that will be helpful. Yeah. So in general, if you don't have match sets, you will just make the treatment history smaller, so you will tend to have more.
Perfect. Just as a quick practical question, could you construct this as a covariate in the sense that you match on an indicator that says something like, instead of matching on cases treated in exactly 1984 with a pre-treatment history of 0001, that you say treated in the 1980s and has at most 10% treated years in the 5 years leading up to, or in the 10 years leading up to the actual treatment.
Right. So in that way, if you construct that covariate, you will just set the L to 1, right? So that you have the shortest history, so that you have a bunch of matches, and then you control for that covariate, so that kind of information is still sort of adjusted for. Yeah, you can do that. Yeah.
Perfect. We have one final question that I received via DM. And the person prefaces that question by saying that they may not have understood it correctly. But the question is, when using the Mahalanobis distance for matching, you choose 5 controls being closest to the treated unit. So why aren't they weighted afterwards, as in the propensity scoring case, given that they're still differently close?
Right. So that's just our that just like our decision. And by the way, so propensity, like I don't have the exact answer, but essentially the conventionally people don't use Mahalanobis distance for weighting. Like once they have the distance, they pick the top J, right? Like I'm talking about the whole matching literature, right? Like only when you have scores, you use weights. So that's just the convention. So that's sort of what we follow here. Yeah. So if you want to use weights, you will use like propensity score. Yeah. So people don't, Mahalanobis distance is really sort of, I haven't seen many applications where like people, once they come up with a distance, they inverse weight the distance. So that hasn't been done conventionally, and that's sort of what we follow. Yeah.
Okay, perfect. Thank you so much, Erik, for the presentation and for answering all the questions during the Q&A. Thanks to our audience members for being here and for asking all these great questions. The Social Science Data Lab will be back on October 26th with Eva Achterholt, who will talk about fairness in machine learning. All right. Thanks again, and we hope to see you soon. Bye-bye.
Yeah, thank you very much.